Hi, this is Miss Erickson, and today we're taking notes on conservation of energy. So get your packets, a pen or pencil, and when you're ready, press play. Conservation of energy. The law of conservation of energy states that energy cannot be created nor destroyed, only changed to another type. So a couple things. First of all, a law in physics means that this is always true. Always, always, always. So energy can never, ever, ever be created, can never, ever, ever be destroyed, but it does change from type to type. So we have some examples here. So this ice cream cone, food is a type of chemical energy. So when you eat your food, your body turns it into kinetic energy, to motion energy. Radiant energy, they're calling this radiant energy. I would call it electromagnetic energy, very similar. So electromagnetic energy from the sun, the tree, the leaves on the tree do photosynthesis and turn that energy into chemical energy. Gasoline is a chemical. Your car converts that to energy of motion or kinetic energy. Electrical energy, your stove can turn, if you have an electric stove, it can turn that electricity into thermal energy. So these are all examples of energy being changed into another type. Sometimes we talk about losing energy. We're not really losing it. We're just changing it to other types. The way that we use this, the way that this is applicable in our everyday life is that the total energy in the system remains the same. It is converted between different types of energy. So this is another way of saying the same law. So we have some examples here. So this biker going up the hill, if you're going to go up a hill, you want to get a big head start, right? So you want to bike really fast to start. So you start with a lot of kinetic energy. And then if you stop pedaling, as you go up, that kinetic energy turns into potential energy. And then maybe you have some kinetic energy left. Maybe you're still going very slowly, a small amount of kinetic energy at the top, but it's mostly potential energy because you're way up high at the top of this hill. And then as you go down the hill, you lose potential energy, but you gain kinetic energy. So in this example, we're switching between kinetic and potential energy and then back to kinetic energy. The same thing happens when you throw a ball up in the air. The maximum kinetic energy is at the bottom. So when you throw that ball up, you have to give it a big force so that there's a lot of velocity. So the moment it leaves your hand, right, one tiny fraction of a moment after it leaves your hand, it's going to have a lot of kinetic energy. That's when it's going the fastest because you need to give it a ton of speed for it to go up. And then as it goes up, it's going to slow down. So as it slows down, it has less and less kinetic energy, but it's going higher and higher and higher up. So it has more potential energy. And then as it comes back down, it's losing potential energy and gaining kinetic. So in both of these cases, as it goes up, it loses potential. And as it comes down, as it goes up, it gains potential, loses kinetic. As it goes down, it gains kinetic, loses potential. So it's switching back and forth between potential and kinetic. Now you can have both at the top. If it's going straight up, it's going to stop and not have any kinetic at the top. But if it's going up and over, at the top, it still has some kinetic energy at the top. And likely this biker has a little bit of kinetic at the top. We are going to see examples like this. So I would draw a picture of this ball going up, and I would label the bottom maximum kinetic energy, minimum potential energy. Label the top maximum potential energy, minimum kinetic energy. So I would have this picture in your notes. This is another example of how we would actually use conservation of energy to solve problems. So we have this little guy here. He's going to jump down into this little bucket of water. Do not try this at home. I hope I don't have to say that. But we know we found his mass and we found the height and we did some calculations. We found his potential energy at the beginning is 15,000 joules. And because he's just standing here, he's not moving yet. His kinetic energy starts at 0. Now, as he falls down, if we ignore air resistance, so pretend there's no air resistance, that potential energy is going to be converted into kinetic as he falls down. So the question is, how much kinetic energy does he have at this point? How much kinetic energy does he have at this point? And so on. So the answer is the total. I know the total energy is 15,000 joules because he started with 15,000 joules of potential, 0 kinetic. So the total at the top was 15,000. So the total always has to be 15,000. So here he has 11,250 joules of potential, and then we don't know how much kinetic yet. So potential plus kinetic equals the total. So that's going to be, I subtract it over, this is going to be 3,750. So pause, see if you can find the missing energies before me. And again, this is a good example to have in your notes. And you don't have to draw this picture, but I would draw a stick figure, and I would draw the stick figure at various different heights, because this is a good example to have in your notes. Okay, if you haven't yet, press pause, get those answers, and then press play when you have those answers. And 7,500 here. So here it's half potential, half kinetic. Here it's more kinetic, 11,250 kinetic, less potential. And then at the very bottom, it's all kinetic for just a moment. And then when he hits, it's going to change to a different type of energy. There might be a lot of different kinds of energies happening there when he finally hits. With these problems, we're always going to look right before he hits the ground, because after he hits the ground, that's a very complicated problem. So this kinetic energy at the bottom, we're talking about the kinetic energy just milliseconds, just moments before he hits. Here's another type of example. What energy conversions happen during this pole vault? So what kind of energy, first he starts running. What kind of energy does he have when he's running? That's kinetic energy. And then the pole, when he puts the pole in, he's going to bend the pole. And I don't think we've talked about this type of energy. This is a different type of energy. The pole, when it bends, it's going to store. This is a different kind of potential energy, because that pole is storing that energy. When it snaps up, it's going to push him over the top. That's elastic potential energy. We're not going to spend a lot of time on elastic potential energy, but basically think of it as like a rubber band. It's a little different than a rubber band, but it's the same kind of, you're pulling it back, and then when you let go, it's going to snap. And when it snaps, it's going to release that energy. So all of that stored energy in the pole that's going to snap is elastic potential energy. And then at the top, when he's really up high, that's going to be gravitational potential energy. So when we say potential energy, we usually are talking about gravitational potential energy. So when he's up high, it's gravitational potential energy. If you just say PE, that's good enough for me, because that's the main PE that we talk about. Here we have another example of conservation of energy. This would be a math type problem. So at a construction site, 1.5 kilogram brick is dropped from rest and hits the ground at a speed of 26 meters per second. Now we know that's just before it hits the ground. 26 meters per second is right before it hits the ground. Assuming air resistance can be ignored, calculate the gravitational potential energy of the brick before it was dropped. So we see these numbers, so we're going to start with our 4 steps. So we have mass and velocity, and then the question is, what is the PE? So this is where a lot of people are going to get stumped. A lot of people are going to say, well, we don't have the height, so how can we find the PE? And the answer is conservation of energy. So we started with the brick up high, and then it started with potential energy, and then as it fell, that potential energy turned into kinetic energy as it sped up. So if we find the kinetic energy, we will actually be that the kinetic energy right before it hits the ground is equal to the potential energy at the top of the hill. That's how we use conservation of energy. So even though the question is asking for PE, we're going to find the KE. So we're going to use our formula for KE, plug our numbers in, and like I said, this kinetic energy at the bottom is equal to the potential energy at the top. So that's how I can do this tricky thing where it asks for PE, but I find KE. Okay, so in our previous examples, in all of the examples that we were talking about, we were ignoring friction. So when you throw a ball up and it comes back down, when you ride your bike up a hill and you coast back down. In that example, when you dropped the brick, we were always ignoring friction. And it's really helpful to ignore friction because then the energy just goes K-E-P-E, K-E-P-E. It just goes back and forth, and it's really easy to keep track of it. But in the real world, we can't ignore friction. So what happens when there is friction? Work done by friction changes kinetic energy into thermal energy. So if you rub your hands together, they get hot. That friction between your hands is changing that kinetic energy. I'm moving my hands. I've got a lot of kinetic energy into thermal energy. Friction is a major cause of energy consumption in cars and factories, and falling objects convert most of their PE into thermal energy from friction and the rest into KE. So the second one here, falling objects, we talked about if you throw a penny off the top of the Empire State Building, if you could ignore air resistance, if there was no air resistance, that penny would continue accelerating and getting faster and faster and faster. That potential energy from being up so high would give it enough kinetic energy at the bottom that it could kill somebody. But since we can't ignore air resistance, we can't ignore friction, most of that energy actually turns into thermal, and the penny would not actually hurt anybody. Well, it might hurt, but it would not actually kill them. Just leave a nice big bump on their head or wherever it hits. And then this part, friction is a major cause of energy consumption. So trying to make cars that are more fuel efficient, trying to make anything that is more fuel efficient is really trying to minimize friction, trying to minimize that extra thermal energy, aerodynamics, any of that can help reduce the amount of energy we need by reducing the amount of friction. And last example, so some of these examples, again, write this down. So these are types of other questions I could ask. So I could say an electric motor, what kind of energy does it start with and what kind of energy does it end with? So an electric motor, anytime you see the word electric, it's going to start with electrical energy from electricity. So you could say electrical, you could say electric, you could say electricity. All of those would be good answers for starting energy. And a motor is something that moves. So anytime you see the word motor, that's going to be kinetic because it's moving. So I don't know what that electric motor could be in a lawnmower, it could be in a car, it could be in a fan, it could be in a blender. Anything that's moving could have an electric motor. So press pause, see if you can get the rest of these before I give you the answer. Some of them are a little tricky, so if you don't know like what kerosene is, just skip it for the moment and see if you can get the rest. And then once you have them all, press play. Okay, so some of these are pretty straightforward, like a toaster. You plug a toaster in, so anything that you plug in starts with electric. Light bulb, you could call this light energy. I call it electromagnetic. And then I said in parentheses also thermal, because light bulbs tend to get very hot. So the thermal is not the energy we want. So that's another example of wasted energy. We don't want thermal energy to come out of our light bulbs, but it does. Hair dryer, I said thermal and kinetic. So there's heat in a hair dryer, but it's also blowing, all of that blowing wind, that's kinetic. Kerosene is like a type of gasoline. It's a little difference. So it's light and thermal. Calculator is a little tricky. If it's battery operated, batteries are chemical. And then solar powered, it's electromagnetic. Oh, and I forgot the answer is going to be electromagnetic. It's electrical. And if you said electrical or electromagnetic, either of those would work. Calculator is kind of a different sort of answer, depending on what kind of calculator it has. Plants start with lights and end in chemical. Any food is all chemical. So that's our last example. So you should have all your notes. If you don't, go back, rewind, and get the notes you need. Now that you have your notes, make sure you get your 3 questions and then your summary at the bottom. A lot of people are missing easy points. These questions and summaries are worth points, so make sure you're doing them. If you